let's talk about some basic adjectives we use to describe matrices. The first adjective we'll talk about here is called square. An m by n matrix is called square if m equals n. Well, what does this mean? This just means that the number of rows is the same as the number of columns. So we have three archetypes for shapes of matrices here. If we look at the first one, if we count the number of rows, we get 1, 2, 3. And if we count the number of columns, we get 1, 2, 3. Number of rows is the same as the number of columns. So whatever the entries are, we would call this matrix square. If we look at our second matrix here and count the number of rows, we would find that there are 4. And if we count the number of columns, we also find there are 4. 4 rows, 4 columns, we call this matrix square. If we look at our last shape here, though, this matrix has 3 rows and 4 columns. This is a perfectly good matrix. We just don't use the adjective square to describe this matrix. So we would say this is not a square matrix. Okay, great. Another important thing that we need to cover is the notion of the diagonal of a matrix. The diagonal of a matrix refers to all of the entries in the matrix where the row index matches the column index. So if you were to write down all of the entries in the matrix with subscript notation, these would be all of the entries where the row subscript matches the column subscript. So I have a 3 by 3 matrix here. When we use the term the diagonal of this matrix, or when we talk about the diagonal of this matrix, we're talking about the 1, 1, 2, 2, and 3, 3 positions of this matrix. Here I have a matrix B. This looks like a 4 by 3 matrix. When we talk about the diagonal of this matrix, we're referring to the entries in the 1, 1, 2, 2, and 3, 3 positions. Here I have another matrix called C. This is a 3 by 4 matrix. When we talk about the diagonal of this matrix, we're talking about the 1, 1, 2, 2, and 3, 3 positions in this matrix. So the diagonal is often useful in its own right, but it's also an interesting reference point to sort of orient yourself when you're talking about entries inside of a matrix. Now, this allows us to talk about some interesting, new interesting adjectives. One thing that'll come up a lot is the notion of a triangular matrix, of which there are 2 types. The first type is called upper triangular. The term upper triangular means every entry below the diagonal equals 0. Let's look at some examples. So in our first example here on the left, we're looking at a 3 by 3 matrix. So this is a square matrix. If I look at the diagonal, that would be the 1, 1, 2, 2, and 3, 3 positions. If I'm curious whether or not something is upper triangular, what I'll do is I'll section off everything on the diagonal and above, and I'll check that everything outside of that section equals 0. In this case, everything below the diagonal equals 0, so I would call this matrix upper triangular. The idea here is that wherever something is not 0 in an upper triangular matrix is concentrated either on the diagonal or above, which cuts out this sort of triangle shape pointing up. Also note here that we are not making any judgments in an upper triangular matrix what can happen on the diagonal or above. You'll note that on the diagonal there's a 0. That's perfectly acceptable. What's required of an upper triangular matrix is simply that everything below the diagonal equals 0. If we go to the next matrix, this one's a 4 by 3. If I section off everything on the diagonal and above and look outside of that section, I find that everything equals 0. So this is called an upper triangular matrix. So that's an upper triangular matrix. If I go to my third example, this is a 3 by 4 matrix. When I section off everything on the diagonal and above and look outside of that section, I find a problem. There's a 9 here, and that 9 is outside of the section. That's in the 3, 1 position. That 9 is not 0, so we say this matrix is not upper triangular. Now, if you want a more mathematical way of defining the notion of being upper triangular, what we're doing is we're stipulating that every ij entry where the row index is greater than the column index must be equal to 0. So that's maybe a more sophisticated way to refer to this more intuitive concept that we're referring to when we talk about upper triangular matrices. Of course, if we're going to talk about upper triangular matrices, it might also make sense to talk about lower triangular matrices. These are the matrices where every entry above the diagonal is equal to 0. On the left here, it looks like we're studying, what, a 4 by 5 matrix. If I section off everything on the diagonal and below and look outside of that section, I find that every entry equals 0. So this is a valid example of a lower triangular matrix. On the other hand, if I go to my, let's see here, this looks like a 5 by 4 matrix on the right, I can section off everything on the diagonal and below and look at everything outside of that section. Well, here, there's a 5 in the 2, 4 position. 5 is not 0, so this is not a lower triangular matrix. Again, if we want a more mathematical way of getting at this concept, the idea here is that we're requiring every entry, every ij entry, where I is less than j, so every where the row index is less than the column index, we're requiring those entries to equal 0 in order for a matrix to earn the title lower triangular. So some matrices are upper triangular, some matrices are lower triangular, some matrices are neither. Now, we've seen the term diagonal before when we're talking about something that a matrix possesses. That's all of the entries where the row index matches the column index. But we can also use the term diagonal as an adjective to describe certain kinds of matrices. We call a matrix diagonal, so we use the term diagonal to describe a matrix, if everything above the diagonal and everything below the diagonal equals 0. On the left here, we have a 3 by 3 matrix. If I section off just the diagonal, I realize that everything that's not on the diagonal here equals 0, so we call this a diagonal matrix. Over here, I'm looking at a 4 by 3 matrix. Again, if I section off the diagonal and look at everything outside of the diagonal, I realize everything equals 0, so I would call this second matrix a diagonal matrix. In my third example, though, when I section off the diagonal, I find that there's an entry not on the diagonal in the 1, 3 position that's not 0. That's this 7. 7 is not equal to 0, so this is not a diagonal matrix. You will notice, however, that this matrix all the way on the right is an upper triangular matrix. So that's an example of an upper triangular matrix that's not diagonal. So if you wanted a mathematical way to do this, you could say that to require a matrix to be diagonal is to require every ij entry to equal 0 where I is not j, so the row index doesn't match the column index. Note here that matrices that are diagonal are both upper triangular and lower triangular. Everything below the diagonal equals 0, so they are upper triangular. Everything above the diagonal is 0, so they are also lower triangular. Now, sometimes we'll want to efficiently define a diagonal matrix. This will be particularly important, actually, in sort of the third part of this course. One way to efficiently do this is to use this diag notation. When we write diag and then list n scalars, what we are referring to is the n by n diagonal matrix, where the entries on the diagonal are these numbers d1 through dn. Here's an example to illustrate the point. Here I'm writing diag of 4, 0, negative 7, 12, 5. So what I'm referring to here, how many scalars are there? 1, 2, 3, 4, 5. I'm referring to a 5 by 5 matrix where the entries on the diagonal are 4, 0, negative 7, 12, and 5. So those are the diagonal entries, and everything else equals 0. Now, when there are lots of 0 entries in a matrix, sometimes what we do is we just omit those entries for efficiency. So whenever there are blank entries in a matrix, those blank entries are understood to equal 0. So when we write something like this, 4, 0, negative 7, 12, 5, cascading in a diagonal from the upper left-hand corner to the bottom right-hand corner, the idea is that this is a 5 by 5 matrix where all the other positions equal 0. Great. There is a notion of 0 when we're talking about either vectors or matrices, but the size is important here. For example, so there's a notion of a 0 vector, regardless of the number of coordinates we're talking about, and there's a notion of a 0 matrix, regardless of the number of rows or number of columns we're talking about. What I mean when I say regardless of number of rows or number of columns or number of coordinates is that if we're working in R2, so if we're working with vectors with 2 coordinates, there is a notion of a 0 vector. That's simply the vector where there are 2 zeros. If we're working in R4, we might use the subscript, the notation bold O sub 4 to refer to the vector with 4 zeros in it. And if we're working with matrices, we'll use bold O sub m by n to refer to the number of rows and columns. So bold O sub 3 by 2 refers to the 3 by 2 matrix where all of the entries equal 0. Bold O sub 4 by 4, for example, refers to the 4x4 matrix where all entries equal 0. Now, it is sometimes the case that it is clear what the context is. So it might just be clear that the only conversation, or in our conversation, the only object of interest is a vector with 2 coordinates. If that's the case, we might just write bold O, and the subscript is sort of inferred from the context. And another extremely important class of matrices is the class of identity matrices. So the n by n identity matrix is notated as capital I sub n, and this is the n by n matrix that has 1s on the diagonal and 0s everywhere else. So if n equals 2, we would be, in this context, we would be studying the 2 by 2 identity matrix. This is the 2 by 2 matrix where the entries on the diagonal are 1 and everything else is equal to 0. If we're working with the with n equals 3, we could talk about the 3 by 3 identity matrix. That's I sub 3. This is the 3 by 3 matrix with 1s on the diagonal and 0s everywhere else. And if n equals 4, the 4 by 4 identity matrix is I sub 4. That's the 4 by 4 matrix with 1s on the diagonal and 0s everywhere else. So it's extremely important that we acquaint ourselves with identity matrices because these come up all the time in matrix theory. Now, one thing the identity matrices allow us to do is talk about what's called the standard basis of Rn. These, so the standard basis of Rn are vectors that are notated as bold E sub 1 all the way down to bold E sub n. And these are referring to the columns of the n by n identity matrix. So if we're talking about vectors in R2, we might talk about the standard basis of R2. That would be referring to the 2 columns, E sub 1 and E sub 2, of the 2 by 2 identity matrix. If we're working in R3, we might talk about the standard basis of R3. Those are the 3 columns, E sub 1, E sub 2, and E sub 3, of the 3 by 3 identity matrix. If we're working in R4, we might talk about the standard basis of R4. Those are the vectors E sub 1, E sub 2, E sub 3, and E sub 4, defined as the 4 columns of the 4 by 4 identity matrix. So when we're talking about the standard basis, it should always be understood in context what n is. If it's 2, then there's 2 standard basis vectors of R2. If it's 3, then there's 3 standard basis vectors of R3, so on and so forth. And finally, I can't help myself, but I can't help but include something maybe a bit more interesting here. Another adjective, which we'll understand a little bit better in a few weeks, but is worth bringing up now, is this adjective called rank 1. So rank 1 is an adjective we ascribe to a matrix when that matrix is not the 0 matrix. So we have to have at least one entry in the matrix that's not 0. And we use the adjective rank 1 when every column of that matrix is a multiple of one of the other columns in the matrix. So, the idea here is that every column can be viewed as a scalar multiple of one column in the matrix. So here's an example. Here are some examples illustrating the point. Here we have a 4 by 3 matrix. If I look at the first column here, the coordinates are 2, 5, 3, 6. Well, the next column of this matrix is 6, 15, 9, 18. If I look closely at this, I might realize that 6 is really 2 times 3, 15 is 5 times 3, 9 is 3 times 3, and 18 is 6 times 3. So the idea here is that the second column in this matrix is really just 3 multiplied by the first column. So to get the second column of this matrix, we scale the first column by 3. If I go to the third column is negative 2, negative 5, negative 3, negative 6. Well, negative 2 is just negative 1 times the first column, or times the first entry in the first column. Negative 5 is the negative of the second entry in the first column, so on and so forth. What we're realizing here is that the third column of this matrix is just negative 1 multiplied by the first column. So all of the columns of this matrix are scalar multiples of the first column. That means that this matrix is a rank 1 matrix. If I go to my second example here, in my second example, I have a column of zeros. And then if I look at the second column, the entries are 7, 14, 1, 5. So the second column I'll label as col sub 2. The first column is technically a multiple of the second column here. the first column is just 0 scaling the second column. So, so far this is actually on track to being rank 1. The first column is a scalar multiple of the second column. But when I look at the third column here, I don't know what I need to multiply 7 by to get -3, but it's certainly not the same thing I would multiply 14 by to get 0. That would be 0. So this third column is not a scalar multiple of the second column. The first column was, but the third column isn't. So this second matrix here is not a rank 1 matrix. So in this scenario, A is rank 1, but B is not rank 1. That's the most sophisticated adjective that we're introducing here. We'll do a lot more with this adjective rank later in the course, but I just think this is a cool opportunity to introduce the concept. Also, if we go to the agenda for the course, if we go to the adjectives lesson and click on the Sage applet, we'll find 2 calculators here that recognize that Sage is intelligent enough to understand our adjectives. Typically, if you're working in this syntax, the idea is that if we define a matrix maybe called A and write dot property name, whatever the property is we're interested in, open parentheses, close parentheses, Sage can tell us whether or not the property applies to the matrix. So here I've predefined a matrix called A. It looks like this one has 3 rows, and each row has 3 entries, so this is a 3 by 3 matrix. And I have 4 print statements down here. The first one will tell us the number of rows, and the syntax is a.in rows. The second print statement tells us the number of columns. This is the syntax here is a.in cols. The third print statement tells us whether or not this is a diagonal matrix. The third print statement will tell us what the diagonal of this matrix is. And the fourth print statement will tell us whether or not this is a symmetric matrix. That's an adjective we learned previously. So if I click evaluate, so this matrix I've defined has 3 rows, 1, 2, 3, 4, 5, 6, 7, 8, 9. The print statements are telling us that the number of rows is 3 and the number of columns is 3. That's what we expected. The diagonal of this 3 by 3 matrix consists of the scalars 1, 5, and 9. And I'm asking in the fourth print statement whether or not this is a symmetric matrix. Well, the answer here is false. This is not a symmetric matrix. The second calculator here introduces a few interesting matrix constructs. We can construct a 0 matrix, a 1s matrix, an identity matrix, or even a diagonal matrix in Sage. And so if we click evaluate here, we'll find that we're employing that syntax to define particular types of matrices. The first syntax here defines the 3 by 4 0 matrix. So that syntax was 0 underscore matrix, open parentheses, 3 comma 4. So this gives us the 3 by 4 0 matrix. The next thing, print statement, gives us the 6 by 3 1s matrix. So here we're inputting 1s underscore matrix 6 comma 3 to produce a matrix that has 6 rows and 3 columns where every entry equals 1. We also have defined the 9 by 9 identity matrix here by using the syntax identity underscore matrix 9. So that gives us the 9 by 9 matrix where all of the entries are 0 except the diagonal entries, which equal 1. And the last piece of syntax we've used is diagonal underscore matrix -795. This should produce the 3 by 3 matrix where everything is 0 except the diagonal entries, which should be -795. And if we go to the bottom here, we see that's exactly what we've produced.